Welcome to This Explainer. I'm so glad you're here, because today we're diving into something you've probably stared out of dozens of times without giving it a second thought. We're looking at the hidden, honestly high-stakes engineering behind airplane windows. Yep, today we're uncovering the engineering legacy of the de Havilland Comet and figuring out exactly why airplane windows are round. It's a crazy story of ambition, invisible physics, and how one tiny little detail completely altered the course of human flight.
So, let me ask you, have you ever actually stopped to wonder why they're round? At first glance, it just seems like a stylistic choice, right? Maybe it just looks cooler or more aerodynamic. But I promise you, it's anything but aesthetic. This simple, curved shape actually comes from one of the absolute deadliest engineering mistakes in all of aviation history. It's a design born entirely out of necessity, a mistake that literally caused seemingly perfect airplanes to break apart in midair.
To really appreciate how weird this is, just look around you. Think about your house. It's got square or rectangular windows. You get into your car, rectangular windows with sharp corners. You walk past a skyscraper, and it's basically a giant towering grid of perfectly sharp 90-degree angles. Sharp corners are literally everywhere in human architecture. So when you look at it that way, the smooth curves of a passenger jet's windows stand out as this glaring exception. There has to be a pretty profound reason why the standard rules of design completely go out the window, pun intended, the minute we leave the ground.
All right, let's talk about the environment up there. 35,000. That is the altitude, in feet, where you're typically cruising on a commercial flight. And at 35,000 feet, the environment right outside that window is incredibly hostile. We're talking outside temperatures plunging to a freezing minus 50 degrees Celsius. On top of that, the air is so unimaginably thin that humans literally cannot survive without supplementary oxygen. Yet, there you are, sitting inside in a t-shirt, sipping on a coffee, maybe even taking a nap. So how is that even possible?
The answer, of course, is cabin pressurization. Basically, the plane maintains the air inside the cabin at a much higher pressure than the super thin air outside. This creates that wonderfully comfortable environment for us passengers. But, and this is a massive but here, it also creates this immense, constant force, pushing outward on the aircraft's entire body. During every single flight, that huge pressure difference repeatedly expands and then contracts the fuselage. Think of it kind of like a giant balloon inflating and deflating slightly. Thousands and thousands of times over its lifespan, just stretching and squeezing year after year.
Which brings us to the early days of commercial aviation. This was a time when engineers were honestly still figuring out exactly how aircraft behaved under these extreme repetitive conditions. Enter the de Havilland Comet in the early 1950s. This was the world's very first commercial jet airliner, and it was a total marvel. Passengers loved it because it flew higher, faster, and way smoother than any clunky old propeller plane before it. It looked like the literal future. But in 1954, that dream turned into an absolute nightmare. Multiple Comet aircraft, mysteriously and tragically, just disintegrated in midair. No warning for the passengers, no warning for the crew. The planes just vanished from the sky. And as you can imagine, the entire world was completely shocked.
Investigators were absolutely desperate for answers. I mean, how could the most advanced passenger jet ever built just fail like that? Well, it turns out, hidden right there in its sleek, futuristic design was a fatal flaw: large, square windows. Now, at the time, nobody thought twice about this. Like we talked about earlier, square windows were just easier to manufacture, and to the engineers back then, they looked completely normal. But what those brilliant engineers didn't quite grasp yet was how that repeated, high-altitude pressurization was interacting with that specific, sharp geometry.
Because here's what was actually happening. Every single time that cabin was pressurized, stress was silently building up right around the sharp corners of those square windows. Over time, these tiny little cracks started to form. And the truly terrifying part, these cracks were microscopic, completely invisible to the naked eye. Maintenance crews couldn't see them during their regular inspections. The pilots had absolutely no idea they were there. But with every single pressurized flight, every time that metal tube expanded and contracted, those invisible cracks grew just a tiny bit larger, slowly destroying the very integrity of the fuselage.
To figure all this out, investigators had to launch one of the most unprecedented accident investigations in history. They needed to recreate the brutal stresses of flight without, putting anyone's life in danger. So they came up with this unbelievable method. They took an entire full-sized aircraft and put it inside a giant water tank. Then they repeatedly pressurized it using water to simulate years and years of flying, all squeezed into a vastly shortened time frame. And eventually, inside that massive tank, the metal finally gave way.
That's when they discovered the absolute, undeniable truth about where the failure started.
This brings us to the core physics behind the tragedy, and there's a great way to picture it. Just imagine bending a piece of paper. A tear is so much more likely to start from a sharp corner than from a smooth, continuous curve. The crucial point here is that stress just does not spread out evenly around sharp corners. Instead, it violently concentrates right at the point of the angle. So when you take a square window and repeatedly blast outward against it with atmospheric pressure, those four sharp corners basically become incredibly dangerous focal points for structural stress.
The contrast between these two shapes is just stark. On one hand, with sharp corners, stress heavily concentrates at specific, pinpoint locations, weakening the metal until you get a catastrophic failure. But on the other hand, with smooth curves, that stress naturally distributes itself evenly across the entire structure. A round or oval window is vastly safer because instead of pressure building up violently at a 90-degree angle, the forces literally just flow smoothly around the edges. It's a simple shift in geometry, but it dramatically and permanently reduces the risk of those microscopic cracks ever forming in the first place.
Let's fast forward to the aircraft we fly on today. Getting rid of the square shape was the foundational fix, but modern airplane windows have evolved into these absolute marvels of layered engineering. You're not just looking through one piece of curved glass anymore. They actually consist of multiple, completely separate panes layered together. This hardcore composite design is required to withstand those massive pressure differences, handle wild temperature swings from runway heat all the way down to -50 degrees, and even resist sudden mid-flight impacts.
And tucked away within that complex, multi-layered system is another mind-blowing little detail. Have you ever noticed that tiny little hole at the bottom of the airplane window? A lot of people think it looks like a defect or a scratch, but it is deeply, highly intentional. It's called a bleed hole. Its entire purpose is to meticulously regulate the air pressure between the different layers of the window panes. That ensures the structural stress is managed perfectly, significantly reducing the load on the outer pane. It just goes to show that up at 35,000 feet, every single detail has been carefully, relentlessly engineered. There are simply no accidents in modern aviation design.
Which leaves us with a final question for you to ponder. Will you ever look at a round airplane window the exact same way again? Millions of us fly safely every single day without giving a second thought to the shape of the frame we're looking out of. Yet that simple, rounded curve is this profound reminder of an incredibly important lesson. Sometimes the absolute smallest details matter the most. A single sharp corner, a tiny, invisible crack, a totally, seemingly harmless design choice. That was all it took to change aviation forever. So the next time you snag that window seat, take a closer look. That curve isn't there for style. It's there because brilliant engineers learned, through immense tragedy and relentless innovation, exactly what it takes to keep us safely suspended in the sky. Thank you so much for joining me on this explainer, and I'll catch you next time.